Welcome to another lecture where we will continue our discussion of Unit 4, which has to do with momentum. So last time we introduced this conservation law where we said that if there are no external forces on a system, then the linear momentum of that system is going to stay constant. Now, one thing that I didn't mention last time is how this is essentially a consequence of Newton's second law. If you think about what the definition of momentum was equal to mass times velocity. What would constitute a change of momentum? If we assume that the mass of the system remains unchanged, or the objects in the system remain unchanged, then when you have a change of momentum, that amounts to some sort of change of velocity. So, if I substitute that into this right-hand side of the equation here, you see that I have delta v over delta t, which essentially is an acceleration, and we get back Newton's second law, F equals m times a. Okay, so anytime this left-hand side of the equation is equal to 0, then the only thing that can make that 0 is if my change of momentum is also going to 0. So that's why you can really think about the law of conservation of linear momentum as a consequence of Newton's second law. All right, and we said that typically one major application we're going to look at in terms of the law of conservation of momentum are collisions. And we defined what is meant by an elastic collision versus an inelastic collision last time. However, it's a little more nuanced than what I described last time. If you want to be more careful about the language here, for something to be completely elastic or perfectly elastic is really sort of an idealization, because you would have to have the condition that both the momentum and the kinetic energy are conserved, and you don't have any sort of losses by way of deformation or heat and so on. We can approximate some things as perfectly elastic collisions. The typical example, like I mentioned last time, is the collision of billiard balls. Most collisions, however, are going to involve some loss of that kinetic energy in the form of deformation or heat or noise as the collision takes place. And so as such, they are actually what we would call inelastic, where the momentum is conserved but not necessarily the kinetic energy. And then for something to be completely inelastic, then what's actually happening is the objects are sticking together entirely, like the example I gave you last time of the two football players effectively becoming one combined mass that has a common final velocity. Okay, so let's take a conceptual example first, and then we're going to take a couple problem-solving examples. Although this one will involve some mathematics if you want to really carefully understand what's going on. So let's suppose we have these billiard balls colliding, and we are in the real world now, and we want to know if this is a perfectly elastic collision or not, or how far off of that we are. So we have a cue ball moving at the speed that's mentioned here. After it collides with a striped ball, it will have this velocity here. And we're just going to take this in one dimension and assume everything moves along the x-axis. So to answer the question of whether or not this is a perfectly elastic collision, remember that the definition of that is that not only is the momentum conserved, but so is the kinetic energy. Of course, the momentum is conserved in all cases, so one tactic I can take to figure this out is to figure out what the final momentum or final velocity of the striped ball is, given the final velocity of the cue ball, and then I can see if in addition to that, knowing all of the velocities, if that's going to allow me to say that the kinetic energy is also conserved. So in other words, I'm going to apply the law of conservation of linear momentum first to figure out what's actually going on, and then I'm going to see if that fits with the idea that the kinetic energy may or may not be conserved. So in the initial state, the momentum of the system is entirely in the cue ball because the striped ball is just sitting there. And so the momentum initially is just going to be the momentum associated with that cue ball, mvc initial. Now, for momentum to be conserved, this has to equal the final state. And the final state momentum is going to be the momentum of each of the balls. So I will have some mv associated with the cue ball final plus mv of the striped ball final. Now, why are these all the same m? Well, I am making an assumption that all of these billiard balls are the same mass. Okay, as you will see when we equate these things, that will simplify my situation to allow me then to solve the problem fairly straightforwardly. So what I'm saying then is that m times v of the cue ball initial equals mv of the cue ball final plus mv of the striped ball final. These masses all cancel, and so I can then figure out what the striped ball's velocity is by subtracting the final velocity of the cue ball from both sides of the equation. And since the cue ball was initially moving at 30 centimeters per second, and afterwards it's moving at 1 centimeter per second, then it's easy to compute that 30 minus 1 will give me 29 centimeters per second for the striped ball. So the question is, will this agree with kinetic energy being conserved? In the initial state, I had 1/2 mv of the cue ball initial squared, and that was the only thing moving, so that was the only thing with kinetic energy. What I want to know is, does that equal 1/2 mv of the cue ball final squared plus 1/2 mv of the striped ball final squared, since those are the kinetic energies in the final state. The 1/2s cancel, the m's cancel again, and so the question becomes, does 30 centimeters per second all squared equal 1 centimeter per second all squared plus 29 centimeters per second all squared? And the answer should be fairly obvious that this is not correct. And so the kinetic energy is indeed not conserved. So this is not a perfectly elastic collision. So the question is now, what would have to be the case for it to be perfectly elastic? For it to be perfectly elastic, you would want the situation that the momentum is completely transferred to the striped ball. In other words, you would want the final velocity of the cue ball to be equal to 0 and the final velocity of the striped ball to be equal to the 30 centimeters per second. And you can check that out in the previous equation here and see that that will check out. If I have a 0 here and a 30 here, then this does equal, the left-hand side does equal the right-hand side, and kinetic energy is conserved. So this should make you think about these Newton's cradle ideas. Whenever we have objects like this that are the same mass and they're colliding with one another elastically, effectively they're transferring their momentum from one to the other. This is approximately true for one of these Newton's cradles and for billiard balls. It's not perfectly true, and there are external forces involved, such as friction, that we're neglecting. But it's a very close approximation to a perfectly elastic collision. I would like you to think about this question, though. What would happen if there were different masses? Instead of the billiard balls being equal in mass, what if one was more massive than the other? And if there was an elastic collision in that case, what would it look like? That's some food for you to think about. I want to move on to a couple more examples. We're going to do 2 more examples in 1 dimension, and then we're going to do a 2-dimensional example. So let's take an amusement park ride, the bumper cars, and let's imagine that we are in this ride and you see that a dad crashes his bumper car into his son's bumper car. And we want to know what the dad's final velocity is compared to the son's final velocity given the information you see here. Now notice that this problem has been simplified for us because it includes the mass of the dad plus the bumper car and the mass of the son plus the bumper car, right? So we don't have to add these up and figure out what they are. Okay, so conservation of linear momentum tells us that the initial momentum of the system should equal the final momentum of the system. We're all in 1 dimension here, so we just need to add up these momenta. In the initial state, we will then have that the dad is traveling at 3 meters per second and the son is traveling at 1 meter per second. Notice that they're going in the same direction. Okay, so the dad is going this way and the son is going this way as well. That will become important because whenever we apply conservation of linear momentum to a situation like this, we need to make sure that we respect the directionality and